All right, so we're going to start talking about specific heat. So, specific heat is the amount of energy that is required to raise the temperature of a unit of mass 1 degree. And remember, the change in temperature is the same in degrees Celsius or degrees Kelvin. So, a change in temperature of 1 degree Celsius is the same as a change in temperature in 1 Kelvin. Specific heat is a property. It's measured and it's tabulated as a function of temperature. And we can do that, we can measure that property two ways. One is if we keep the volume of our mass constant. So again, this goes back to how this property was measured in the first place, not how you're going to use it. Okay. But when they measure specific heat, they take a unit of mass, or one way is to take a unit of mass, so 1 kilogram, and see how much heat they have to add to it to raise the temperature of that mass, of that unit mass, 1 degree. And when it's measured this way, we call it specific heat at constant volume. It's CV. Again, you can use this property in processes that are not constant volume process. The only thing it has to do with constant volume is how it was originally measured. So CV is a function of temperature and it is defined according to the internal energy. So you can see this is the derivative of internal energy with respect to temperature, where the volume is constant or the specific volume is constant. The units here are going to be kilojoules per kilogram K. Sometimes you'll see it written as kilojoules per kilogram degrees Celsius, so don't get confused. We typically write it as kilojoules per kilogram K. You can also measure this by taking a unit of mass and seeing how much heat you have to add to it to increase the temperature by 1 degree, but you keep the pressure constant. So as you can imagine, you're going to have to add a little bit more heat because as it expands, it's going to naturally cool off. Okay. So that's that when you measure it this way, it's called CP, specific heat at constant pressure. And that value will be higher for a gas is going to be higher than the CV value. This is dependent, or this is a function of the enthalpy. So CP as a function of temperature is the partial derivative of enthalpy with respect to temperature, where the pressure is constant. Again, same units as CV's kilojoules per kilogram K, or you can write it as kilojoules per kilogram degrees Celsius. So, all right, so here's our equations for CV and CP. We're going to use these properties, CP and CV, to calculate changes in internal energy and enthalpy for substances in a single phase, so compressed liquid, and not all gases, but for ideal gases ideal gases specifically. So they're valid for any substance undergoing any process, any substance in a single phase. But they're not just used for constant volume processes or constant pressure processes. Like I said, the only thing that specific heat relationships have with constant volume or constant pressure is how they were determined originally, right, during the experiment. So again, the relationships we're going to be using, you can use them whether or not that process is a constant volume or constant pressure process. All right, so if you got a single phase, you have a couple of ways of calculating that delta H and delta U. You can use your thermodynamic tables and look up U values and H values. Now, for an ideal gas, your enthalpy and your internal energy actually only depends on one thing, right? It's just another simplification that we could do with ideal gases, or as a result of making that assumption that we've got an ideal gas. So for air, for example, A22, you've got thermodynamic properties for air. If you assume it's an ideal gas, well, all you need to know is the temperature and you can figure out the enthalpy and the internal energy. I want you to make sure that you note that there's 3 other columns that we're not ready to use yet. PR and VR are not pressure and specific volume. They are what's called relative pressure and relative specific volume. Don't use them. They're not something that we're going to use quite yet. Okay, we will, but not quite yet. The other way that we could calculate delta U and delta H, if you know the functions, CV is a function of temperature or CP is a function of temperature, you can actually do the math and calculate it. It's very accurate. It's more work, but you can do it. We're not going to do it. But the other way that we could do it is assuming specific heats are constant during a process. That simplifies things greatly. So let's look at that. We've got 2 cases that we're going to look at. Number 1, compressed liquids and solids, right? So an incompressible substance. Incompressible means that the density and the specific volume doesn't change. And so delta U could be approximated as CV delta T. Notice the CV and the C. So for an incompressible substance, the specific heats are CP and CV. They're the same value. And that's just because they are incompressible. So it doesn't matter whether you kept the volume constant on purpose because you kept it in a rigid tank, or you kept the pressure constant. Because it's incompressible, that specific volume isn't really going to change. So your CP and your CV, when you measure it, is the same. So sometimes you'll see it written as CV, sometimes you'll written as CP, sometimes it's just C. So don't get confused with that. Delta H looks very similar. It's CP delta T plus another term, or C delta T plus another term, and it's V delta P. So there's it's a little bit more. Do note that that V delta P, um, many times that's maybe if the change in pressure isn't that big, because the specific volume may be very small as well. For an incompressible substance, a liquid or a solid, a lot of times that part is ignored and you just use the CP or the C delta T. Um, the other case that we'll look at is with an ideal gas. So this is one that we'll probably use a little bit more frequently in this class. So ideal gas, assumed with constant specific heats also assumed. So two things together. And in that case, delta U is CV delta T and delta H is CP delta T. So we use that all the time for ideal gases. So when can you make that assumption that specific heats are constant? Because that's a really super convenient relationship to use. Number one, if your change in temperature is not that large, if you're looking at something that's less than several hundred degrees, and that's because your CV and your CP, they're a function of temperature. It depends on what temperature you take it at. So if we look at 300 Kelvin, well, what that represents really is how much energy does it take if you start at 300 Kelvin and you add enough energy to increase the temperature by 1 degree, right? So that CP is how much energy you have to add to 1 kilogram of air, right, air right here, to get it to go from 300 to 301 Kelvin if you keep it at constant pressure. And of course, there's another one for constant volume as well. This is the amount of energy that you would have to add to get it to go from 300 to 301 Kelvin. And that last column K is the ratio between those two values. It's CP over CV. You'll notice, of course, that it's always greater than 1 for an ideal gas because the CP value is always going to be bigger, right? As you add heat, as you add heat to to your I go back here. Yeah, as you add heat during a constant pressure process, as it expands, it's going to naturally want to cool off, and so you end up having to add more heat to increase that temperature to 100 or to by one degree. All right, so we're going to be looking at delta U and delta H's, or looking at using CP and CV relationships to evaluate delta H and delta U between two temperatures. And if we're only looking at a change in temperature of a couple of hundred degrees, it's not going to make that much of a difference. CP really only changes, you see, between 250 and 450 by less than 2%. It's not that big a difference. But if you're looking at a large temperature change, then that change or that variability with specific heat is going to start to make a difference at some point. And so if it's less than a couple of hundred degrees, go ahead and you can assume that specific heats are constant, or it would be safe to assume that specific heats are constant. So what temperature should you take it at? Should you take it at T1 or T2? Well, the best cases that are the most accurate best practice is going to be taking it at the average temperature. So T1 plus T2 divided by 2. Less accurate is at 300 Kelvin. Sometimes we use this to analyze certain thermodynamic cycles, and it's just kind of a convenient value because for those processes or for those cycles, you might be looking at several processes. And so getting an average temperature is maybe a little bit more difficult. Um, but in this class, average temperature between um, T1 and T2, unless you're specifically told, take it at this particular temperature. Okay. Um, so let's see, here we go. The other case is if you have a monoatomic gas, that would be another case where it would be okay to make the assumption that specific heats are constant. And in fact, there's a little line in table A21 at the very bottom. It says, so A21 actually has an equation where you can calculate the specific heat values, albeit on a per mole basis, but you can calculate it. You could see um, as a function of these constants, alpha, beta, gamma. But at the very bottom, it says for monoatomic gases such as helium, neon, argon, Cp is constant over a wide temperature range and is very nearly 5/2 times the universal gas constant. Notice that there's a bar over this. If you see a bar in this text, it means it's on a per mole basis. So as opposed to being kilojoules per kilogram K, it's kilojoules per kilomole K. All right. And then the last case where you can assume that specific heats are constant is if you are explicitly told to do so. And on an exam, I'm going to tell you how I want you to solve it. I'm going to tell you assume specific heats are constant, or I'm going to say don't assume specific heats are constant because I might have a specific way that I want to be able to see that you know how to solve it this way, right? But there we go. But this is the general guideline of in practice. These are the times that you can assume that specific keys are constant and it's not going to give you a huge error. Okay. All right. Well, I hope that was helpful. Thank you for watching and let me know if you have questions.